So far, our pursuit of solving quadratic equations has played out something like this. We've been given an equation like x squared plus 2x minus 15 and have been able to utilize one of a few different techniques to solve it. We could use the quadratic formula, we could complete the square, we could even use the square root property in some cases, or as in this particular instance here with x squared plus 2x minus 15, we could factor. We could recognize that there are two numbers that multiply to negative 15 and add to positive 2, namely plus 5 and minus 3, and use those to factor our expression to x plus 5 times x minus 3. Then setting that equal to 0, we can utilize the zero factor property, which tells us that either x plus 5 has to equal to 0 or x minus 3 has to equal to 0 to then allow us to solve for our solutions, giving us x is equal to negative 5 when we subtract 5 from both sides here, or x is equal to 3 when we add 3 to both sides here. And these two answers, negative 5 and 3, make up our solution set for this equation. In other words, both of those answers, if we plug them back in for x, will make that equation true. And for the most part, this has worked really well for us. It's only when we come to an equation like x squared is equal to negative 9 that we start to run into problems, right? Because x squared equal to positive 9, well, that's something that we know how to handle pretty well. We know that this is going to mean that x either has to equal the plus or minus square root of 9, which is either plus or minus 3. Right, we know this works because 3 times 3 gives us 9. In other words, 3 squared does equal 9, or negative 3 times negative 3 equals 9, right? Or negative 3 squared equals 9. But we can't exactly apply that here. Think about it for a second. What number multiplied by itself is going to give us negative 9? It's not 3. 3 squared doesn't equal negative 9. It's not negative 3, because negative 3 squared doesn't equal negative 9 either. It actually turns out that there doesn't seem to be a number that this will work for, right? Because anytime we multiply a positive number times a positive number, it's going to be positive. But also anytime we multiply a negative number times a negative number, it's going to be positive. So at least as it seems right now, there's no way we could multiply a number by itself and end up with a negative number. In other words, we're going to have a really tough time taking a square root of a negative. Well, at least with the numbers we've been working with, at least until now. And in fact, up until this point, we've actually previously excluded square roots of negatives from the domain of equations and functions that we've worked with. So from the domains of the equations and functions we've worked with. And this is because we didn't have a tool to deal with them. There isn't a way for us to define a result of a square root of a negative in the real number system. So all of our numbers, including whole numbers like 1, 2, 3, 4, 5, and so on, and fractions like 1/2 and 3/8 and 11/4, and even irrational numbers like square root of 2 or pi or e, that whole real number system is still limited in terms of providing a meaningful way for us to define a square root of a negative. And so in this video and in the next few videos, what we'll do is we'll look at a way that we can extend this beyond just the real number system to what we call complex numbers. We don't have a really good way to handle this with the tools we've worked with so far, but if we add this new tool, if we define the square root of a negative, we can start to come up with some meaningful answers to this question, some meaningful solutions to an equation like x squared is equal to negative 9. And so the first thing we'll need to do is define what a square root of a negative is going to be. If it's not a real number, then what is it? And so we can say that the imaginary unit I is defined by I equal to the square root of negative 1. So we are defining the square root of -1, the square root of a negative, as this new number I. It's not something we've previously worked with before. It's not a real number. It's not like an irrational like pi or e. It's not a fraction. It's not a whole number or an integer. It is a new thing that we have to create in order to solve this new type of problem. So we will define the square root of -1 as this new number I. And as a result of this, this would be where I squared is equal to -1. So for the first time, we have the ability to square a number and get a negative result, or take the square root of a negative and get a result. And this might seem confusing at first because in some sense it's a little bit less concrete maybe than like some other real number, right? Like I can pull some books off the shelf and we can count how many books there are here. We can read a portion of that book and measure some fraction of how much we've read. And so in some sense, those real numbers can feel a little bit more concrete, a little bit more tangible, but we are able to step a bit beyond that to define a new number I, which we call an imaginary number, to help us solve some of these problems that we come across in mathematics. And so I think that's pretty neat. Now, there are more sort of tangible applications of this. There are real world elements to I. They tend to focus more in the realm of like quantum physics, which is a bit beyond the scope of this video and truthfully a bit beyond the scope of my expertise. But for now, at least, we'll just remember that I is equal to the square root of -1. It's how we take square roots of negatives. It's how we handle those types of problems. And so, for example, this now gives us the ability to simplify an expression like the square root of -9. Instead of just saying this is undefined as we might have previously, we now can recognize that the square root of -9 can be broken up using our square root properties into the square root of -1 times the square root of 9, which we now do have a definition for. We now have defined the square root of -1 as I. And so we can swap the square root of -1 for I, and this would then be I times the square root of 9. And then of course the square root of 9 is equal to 3, so this would give us a final answer of 3 times I. Now, one thing to be careful here just with the notation is sometimes you might see this written as maybe square root of 9 times I. I would be careful with this just because sometimes it's unclear of where exactly that square root ends, and you want to make sure that you're clear that the I is sitting outside of the radical. And so you'll see I'll tend to write this as the letter I first and then the square root after. We can even see this show up in solutions to equations that are trinomials. For example, solving x squared minus 2x plus 2 is going to give us an imaginary number as a result. We can see this by using the quadratic formula, right? We know x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. Or in this case in particular, -2 for -b, which gives us +2 plus or minus the square root of b, or -2 squared, minus 4 times a, which is 1, times c, which is 2, all divided by 2 times a, or 2 times 1. Then doing the arithmetic, this gives us 2 plus or minus the square root of -2 squared, or 4, minus 4 times 2, or 8, all divided by 2. 4 minus 8 is going to give us a -4. And we now know that the root of -4 can be rewritten as the root of -1 times the root 4, or root 4 times I. And so we'll have 2 plus or minus root -1 times root 4 divided by 2. I'll bring this up here for more space, or 2 plus or minus the square root of 4 is just 2, so this will be 2 times root -1 divided by 2, or because we've now defined I equal to the square root of -1, we know this to be 2 plus or minus 2i, all divided by 2, which we can then simplify by factoring out and canceling a 2, or 1 plus or minus I, right? We cancel a 2 from here, leaving us with 1, and here leaving us with 1, and so we have 1 plus or minus I. And so with our final solution of 1 minus I and 1 plus I, we can see that some quadratic equations have these complex solutions. Now there's going to be a lot more to explore with imaginary numbers. In fact, there's entire courses worth of exploration of imaginary numbers. In the next few videos, we'll focus on operating with them, so adding and subtracting, multiplication and division. But there is one more interesting thing I'd like to share before we wrap up this video, and that's what happens when we take powers of I. First and foremost, we know that I to the 0 is equal to 1, right? Anything raised to the 0th power is equal to 1, other than 0 itself. And so we can also define I to the 0 equal to 1 just as we would with any real number. We know that I to the first is equal to the square root of -1, or for the purposes of this demonstration, we'll just simply write I. We know that I to the second, since it's the square root of -1 squared, is just going to be -1, right? When you square a square root, it just becomes that number itself. And so I squared is equal to -1. But then we can also use that fact to determine I cubed. I cubed would just be I squared times I. Now I squared, as we just saw, is equal to -1, and so this would be -I, right? And so I to the 0 equals +1, I to the 1 is equal to I to the 2 is equal to -1, and I to the 3 is equal to -I. I'll highlight this, but you might be sensing a pattern already. If we go to I to the 4th, well, I to the 4th can be broken down into I squared times I squared, or in other words, -1 times -1. Now, when we multiply two negatives together, we get a positive, so this would be +1. When we look at I to the 5th, that would be the same as I to the 4th times I, or as we just saw, I to the 4th is +1, so this would be +1 times I, or I. And so you may be seeing semblances of that same pattern here. I to the 6th might be a little bit trickier, but if we break I to the 6th down into I squared cubed, then we know that this is just -1 cubed, or -1. Right, and we can do this based on the power rule. We multiply those powers when we take an exponent of an exponent. And then just to round out our pattern one more time through one more cycle, we'll take I to the 7th here, which would be I to the 6th times I, again by those exponent rules, or as we just saw, -1 times I, or -I. And so this gives us a second cycle. And so we can see that this is going to continually cycle through 1i, -1, -I, and then repeat 1i, -1, -I. So as we take these powers of I, it will keep cycling through that same pattern over and over and over. And so even if we were to take I to some really large power like 76, if we follow this pattern, then we would still be able to determine that pretty easily. And so what is this pattern? How can we actually do something like that? Well, we can recognize that when we have a number, an exponent that is divisible by 4 with a remainder of 0, that's going to give us a result of 1. That's like the case of I to the 0 or I to the 4th. Both of those give a result of 1. In the next case, if we were to divide by 4 and have a remainder of 1, like in the case of 1 and 5, that's going to give us a result of I. So 1, 5, 9, 13, 17, any number that is 1 above a number that's a multiple of 4, those will always yield the result of I. If we take an exponent that when divided by 4 gives a remainder of 2, for example, like I squared and I to the 6th, right? 6 divided by 4 is 1 with a remainder of 2. Well, that's going to give us a result of -1. And lastly, if we were to divide our exponent by 4 and give a remainder of 3, like in the case of 3 or 7, well, that's going to leave us with a result of -I. And so for however large of a power, this will always be the case as this cycle will repeat and repeat. So in other words, I raised to the nth power can be determined by the remainder of n divided by 4. If the remainder is equal to 0, in other words, if it divides evenly, I to the n is equal to 1. If the remainder is equal to 1, in other words, if it's 1 greater than a multiple of 4, I to the n is equal to I. If the remainder is equal to 2, in other words, if it's 2 greater than a multiple of 4, I to the n is equal to -1. And lastly, if r is equal to 3, in other words, it's 3 above a multiple of 4 or 1 below a multiple of 4, then I to the n is equal to -I. And so, for example, if we wanted to find I when raised to the 73rd power, all we would need to do is take 73 and divide by 4 and compute the remainder. Well, if we note that 4 times 18 is equal to 72, then we can see that 4 times 18 plus 1 is going to equal to 73. So in other words, 73 divided by 4 is 18 with a remainder of 1. We can reference back to our previous pattern and note that any time where our exponent has a remainder of 1, the result is going to equal I, allowing us to determine that I to the 73 is equal to I. So in other words, since 73 divided by 4 has a remainder of 1, I to the 73 is equal to I. Now all of this might feel a little bit strange at first. We have, after all, stepped outside of the realm of real numbers into the world of complex or imaginary numbers. And so there are certainly some new concepts and ideas and properties that we'll have to wrestle with to get a feel for just how this works. But hopefully this video has helped introduce us so far to the idea of a complex number and I and taking square roots of negatives and what that might mean. And in the next video, we'll look a little bit more with how we can work with these numbers, how we can operate on them and add, subtract, multiply, and divide so that we can get a little bit more comfortable with working outside of the bounds of the real number system. And then maybe as you get more comfortable, that can extend into a class where you get to explore the intricacies of complex numbers in a little bit more detail. In the meantime, let me know if you do have any questions or if there's anything that I can do to help, and I hope you have a great rest of your day.